Hi, welcome back. So today we are going to talk about something called an atwoods machine. And we're going to start very simple and then build on it throughout the semester. So what an atwoods machine is, basically it's a pulley, so it's a circle thing that rotates along an axis, and then we connect it. This one happens to be connected via a string to a ceiling. It is very poorly drawn right here, but there we go. And along this pulley, let's get a crayon, let's get a yellow, orange, that's fine. There is a string that wraps around the top of the pulley like so and comes back down like that. And that string connects generally two objects. I tend to draw boxes. That one's pretty easy. And then we look at how things move and acceleration of these boxes and so on and so forth. So for this unit, we are going to talk about massless, frictionless pulleys. Yes, they are imaginary. They don't exist in the real world, but they are what physicists like to call first-order approximations, which means that, yes, a massless, frictionless pulley does not exist, but it gives us a really good approximation of what the acceleration would be, and for a low friction pulley. And then as we learn how to deal with these more simple kinds of problems, we could add on more complicated concepts like torque and rotational inertia and things like this, but that is saved for AP Physics. Okay, so let's get down to business. Alright, so let's call these masses Mass A and Mass B. And let's say we want to find the magnitude of all the forces acting on Mass A and Mass B and find the acceleration of Mass A and Mass B. Now, since Mass A and Mass B are connected via a string, the acceleration, the magnitude of the acceleration is going to be the same because they're connected. So think of a train. So the front of the train can't move any faster than the back of the train. And even though it may go through some wobbly tracks, the front is not going to be moving any faster than the back of the train. So the acceleration is going to be the same for A and B. Now, if the mass of A and the mass of B are equal, will it move if they're not in the same spot, if they're not level? So A is down here and B is right here. Let's draw a free body diagram. So we have the weight by the earth on A, and we have the weight by the earth on B. And we have the tension by the string on A, and we have the tension by the string on B. Now, since this is a massless frictionless pulley, this tension is going to be the same all the way across because it's the same string. So this tension, I don't want to do a tick mark because they're not their law pairs. They are the same because it's the same string. So this tension and this tension are the same. Okay. So let's do this. All right. So let's say that each mass is 3 kilograms. So it would make each weight 30 newtons. And since there's 30 newtons pulling on each side, the tension is 30 newtons. And since the forces are balanced, there's no acceleration. And if the blocks aren't moving to begin with, they're not going to speed up or slow down, so they're going to stay in the same place. And I will show you this in class, because I don't have the equipment right here to show you on the video. But a more interesting example would be this. So now clearly, oh, let me connect this to the ceiling. There we go. So clearly the masses aren't the same. Well, not clearly, they have different densities, but they're not the same. So we have mass A and mass B. Mass A is small, so let's say it's 3 kilograms. And mass B is larger, let's say 9 kilograms. And let's go ahead and solve for the tension in the string and for the acceleration. So like excellent physics students, this is a force problem, and we begin with a free body diagram. Okay, so the weight of B is much larger. Weight by the earth on B is much larger than the weight by the earth on A. Like so. Now the tensions are going to be the same. Now it's good to notice and mark which way the acceleration is for each object. So A, the smaller one, is going to accelerate up, and B, the larger one, is going to accelerate down. Now remember, the accelerations are the same for each block. The magnitude of the acceleration is the same for each block. The direction is different. So for A, let's get the black pen again. Oh, come on. Here we go. We have the tension's going to be a little bit longer than the weight of A, and it's going to be the same length for B, but it's also going to be shorter than the weight of B. So highlighter, this tension and this tension are the same length, they're the same number. That's why I didn't write tension string A, tension string B, because they are the same tension, so I'll just call them T so we don't confuse things. It's the same string. Okay, so now the next thing that we do is let's start solving for things. Well, if we have the mass, we could solve for the weight. So the weight is 30 newtons for A and 90 newtons for B. And next thing we do is write our F-net equations. So the sum of the forces for A is equal to mass of A times the acceleration equals, then we think, which way is the acceleration? For block A, the acceleration is up. So the force going up is tension, and we subtract the force going the other way, the weight of A. And we plug in everything that we can at this point. So the mass of A is 3, we don't know the acceleration, equals tension, we don't know the tension, minus the weight, which is 30. And that's as far as we could get with that one. So let's do for B. Sum of the forces for B is equal to the mass of B times the acceleration. And for this guy, the acceleration of B is down. So I will bubble that because it's not a force, but it's good to remind us. And then you think, okay, what forces are going in the same direction as the acceleration? In this case, it's the weight of B. And you subtract the forces going the opposite direction. In this case, the tension. And we plug in what we know. So 9 kilograms times A is equal to 90 minus T. Now, at this point, we have two equations. We have two equations and two unknowns, and it becomes a math problem. And these tend to be very simple to solve if you just stack them. So we go 3a equals t minus 30, and 9a equals, and I'm just going to put the numbers over the numbers. So it's negative t, because this is minus t, plus 90. So 3 plus 9 is 12. A is equal, the t's cancel out, yay! And 90 minus 30 is 60. So A, oh geez, 12 goes into 65 times? Yeah. Acceleration is 5 meters per second squared. So that's the magnitude of the acceleration. The tension, we just have to plug it into either equation to solve for the tension. So we'll plug it into both to double check ourselves. So 3 times 5 is equal to t minus 30. So 15 is equal to t minus 30. So 15 newtons is equal to t. 45, excuse me. 45 newtons is equal to t. Let's try this side. 9 times 5 is equal to 90 minus t. 45 equals 90 minus t. 45 newtons is equal to the tension. Yay! Okay. Well, the next video we will do another example of an Atwoods machine. All right. See you then.